Okay, previously we had learned to evaluate a definite integral. We are going to go ahead and do it geometrically. So in problem number 1, the function is x, y equals x, so I can draw that pretty easily. So here's a rough sketch of y equals x, and we're looking at this graph from 0 to 2. So this definite integral is asking us to find the area underneath the curve from 0 to 2. So it's just a triangle, so 1/2, base is 2. The height, since this is y equals x, is also 2. So this definite integral would be 4 divided by 2, which is 2. So this is how we did it geometrically, and we can do the same thing with this one. So the function is y equals 3, and we're looking at this graph from 0 to 4. So this definite integral is asking us to find the area underneath the curve of 3 from 0 to 4, so that would be 4 times 3, which is 12. Now these two we can do this way because we can sketch the picture and it's a linear function. Now we want to be able to come up with another way to come up with this value without sketching the picture all the time, and this is where we're going to use what's called the fundamental theorem of calculus. It allows us to evaluate a definite integral. So you're going to take the antiderivative of the function. So the antiderivative of x would be x squared over 2. And what the fundamental theorem says is you're going to plug in the upper bound and then subtract off what you get when you plug in the lower bound. So this is our notation, this backwards bracket, or you can just use a straight line. So if I plug in 2, 2 squared is 4, 4 divided by 2 is 2, minus, and then I plug in the 0 for x, and that's just 0. Notice we get to the exact same thing that we got when we did it geometrically. This one, same thing. So the antiderivative of 3 would be 3x, and then my bounds are 0 to 4. So I plug in the upper bound first, 12 minus 0, and it gives me 12. Same thing when we did it geometrically. Now, problems like 1 and 2, you can do either way, and you'll get the correct answer. But obviously there are some problems where you can't do it this way, so you have to do it by taking the antiderivative. Like this would be a function, I can't graph and find that area geometrically easily. So I'm going to do this by taking the antiderivative, so add 1, divide by the power. And before I plug in the bounds, I'm going to clean this up to be this. And my bounds are -2 to 3. So if I plug in 3, this is going to give me 27 minus 5 times 3, which is 15. So that's going to be all of this minus, if I plug in -2 for x, that gives me -8. So that's -16. And then when I plug in -2 here, it's a -10. So this becomes a +10. And now let's just clean this up. So I've got 54 minus 15 minus, this would be a -6. And at this point, just do the arithmetic, and I believe this gets me all the way to 45. Okay, same thing here. The antiderivative of the secant squared is going to be tangent, and we're going to evaluate from 0 to pi-4. So the tangent of pi-4 is 1, right? Because sine over cosine, it's pi-4, we're the same. Minus tangent of 0 is going to be 0. So that gives me 1 as my value, okay? Now, let's look at the next problem. This is an absolute value function, and let's do it both ways. So if I give you a definite integral, if you can do it geometrically, you can do it geometrically. I will never tell you which way to do it. You want to do it the way that's the quickest. So this function here is an absolute value function. I know the vertex is at 1/2 because it makes that 0. So it looks something like this. So this is saying find the area underneath the curve from 0 all the way to 2. So basically we're just adding the areas of the two triangles. Okay, the first triangle, let me color that a different color, let's make it blue, would be 1/2. The base is 1/2. The height of this triangle is, when I plug in 0 for x, you get the absolute value of -1, which is 1. So there's the blue one. Okay, and then the bigger triangle would be 1/2. Your base is 3/2. The height of this triangle, what's the y value there? If I plug in 2, notice you get 3. So it would be whatever this is. So that's going to be 1/4 plus, gives me 9/4, which is 10/4, which is the same as 5/2. So that's the value of the definite integral. Now, if you choose to do this algebraically using the fundamental theorem, we do not have a rule for taking the antiderivative of the absolute value. You basically have to think about the two different lines and split it up. So this piece here, this line right here, is really the opposite scenario. So that's going from 0 to 1/2 of the opposite of that 2x minus 1 graph. And then the red line here would be the positive scenario, and that's only going from 1/2 to 2 of 2x minus 1 dx. So if you wanted, you could take the antiderivative of those two pieces separately and add them together. So I think for an absolute value question, doing it geometrically is actually much quicker. I'll start the algebraic piece and you can see. So notice here, I'm going to clean this up first. So this is really this. I'll just do the blue piece. So you have negative 2x squared over 2 plus x. You'd have to plug in the 1/2 the 0, get that number, and then do also the second piece. So there are some problems where it is easier to do geometrically, and an absolute value would be one of those. Okay, let's think about a function like this one, why we cannot use that fundamental theorem of calculus. In order to use the fundamental theorem of calculus, if you look up here, notice it says that it has to be continuous on this interval. Okay, this graph is not continuous at x equals 0, so this fundamental theorem, if you actually do it, you'll get a number, but that number is not necessarily going to be correct. If I ask you to integrate this from 1 to 3, that would be okay, because 0 is where the discontinuity is, so we can go from 1 to 3. So just make sure that there's no discontinuity and your bounds don't go over that continuity. Otherwise, that fundamental theorem will not work.